Hi everyone, welcome to the third lecture on chapter 6. That is our chapter on thermochemistry. Today we are going to cover bomb calorimetry, the enthalpy of a reaction, and we are going to look at how we can use calorimetry to calculate the enthalpy of a reaction. So our first topic is bomb calorimetry. Last time we were talking about coffee cup calorimetry, in which we were putting a piece of hot metal into cold water, and we were using the change in temperature to see the energy transfer between that hot metal and the cold water. And we were saying, since that's a closed system, all of the energy that's being lost by the metal is being gained by the water. Bomb calorimetry is a little bit different. In a bomb calorimeter, we will put usually a solid in this container, and then we will ignite it. And when we ignite it, we're going to see how much energy is released by the burning of whatever's in there, and we're going to monitor that via a temperature change. And we're going to say that all of the energy that's being released during this burning process is going to be absorbed by the calorimeter. And we are going to see that absorption by a change in temperature. So a bomb calorimeter is used to measure the change in internal energy because it's a constant volume system. If you'll remember, we said that the change in internal energy was equal to Q plus W. And W, right, is work, and it's related to pressure and volume, okay? Since we're having a constant volume, we don't need to worry about work, and we can use our delta E value our Q value to directly measure delta E. Okay, so the way that we will do this is we are going to use the calorimeter constant. So this is related to our Q equals MCAT that we were using before, but instead our energy of the calorimeter is equal to the specific heat of the calorimeter times the change in temperature. So we've left out mass here because it doesn't matter what the mass of the calorimeter is. We're just looking at how much energy that calorimeter absorbs in total. So our calorimeter units are joules per degree Celsius. Instead, before we had joules per gram degree Celsius. Okay, so that would be for a specific heat of something like aluminum or water. And the specific heat of the calorimeter constant will be in joules per degree Celsius. So we can measure the energy released during the reaction by looking at the energy that was absorbed by the calorimeter. So we have the energy that's being lost during the reaction, that will be negative, right? Because we're always going to ignite something, it's always going to be releasing energy. So we have a negative Q for the reaction is equal to the positive Q of the calorimeter because the calorimeter is gaining all of that heat that's being released. So let's go ahead and try an example. When 1.550 grams of hexane is burned in a bomb calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. It says if the calorimeter constant is 5.73 kilojoules per degree Celsius, find the change in internal energy for burning 1 mole of hexane. And it says, note the units for change in internal energy are kilojoules per mole. That'll help you out. And always remember that the energy that's being absorbed by the calorimeter is the energy that's being lost by the reaction. So given this information, we can go through and calculate the energy that was absorbed by the calorimeter. So our Q of the calorimeter is going to equal our calorimeter constant times our change in temperature. So we have our calorimeter constant, that's 5.73 kilojoules per degree Celsius. And remember, delta T is always going to be T final minus T initial. So our final temperature is 38.13 degrees Celsius minus 25.87 degrees Celsius as our initial temperature. So when we go ahead and math that out, we're going to get that our Q of the calorimeter, right, the energy that was absorbed by the calorimeter is 70.2 kilojoules. And since that is the energy that's being absorbed by the calorimeter, we know that that is the energy that was lost by the reaction. So it's always going to be equal and opposite. That's what this is telling you here, that the energy absorbed by the calorimeter is equal to the energy lost by the reaction. All right, so now we have our kilojoules, and we need to now go find our moles so that we can solve for delta E, which is in kilojoules per mole. So we have 1.550 grams of hexane, and so if you'll recall from when we were doing nomenclature, hex means that there are 6 carbons, right? This is a hydrocarbon, and ane tells you that they are all single bonded. So that means that our N, for our hydrogens is always going to be 2N plus 2. So here N is 6, so we have 2 times 6 plus 2 to get our hydrogens. Okay, so that would be 14. So we have 1.550 grams of C6H14, which is hexane. And then we can divide by the molar mass, 86.18 grams of C6H14 will give us 1 mole of C6H14. So that tells us that we have 0.01799 moles of hexane. So now we can go ahead and solve for our change in internal energy of our reaction is going to equal, right, kilojoules over moles. So we have negative 70.2 kilojoules, and we have 0.01799 moles. So our change in internal energy for burning 1 mole of hexane is negative, right? If we went and put this in our calculator, we'd get negative 3902 kilojoules per mole, but we need to have 3 significant figures. So this would be negative 3.90 times 10 to the third kilojoules per mole. Okay, so there's our answer. So again, this would be for a bomb calorimeter. We're always going to solve for delta E in kilojoules per mole. So always solve for Q, right, from the information given for the change in temperature of the calorimeter. And then you'll always be given some amount of grams for your substance that was burned, and then you can calculate moles and divide them up, get kilojoules per mole. So our next topic is enthalpy. So enthalpy is the sum of the internal energy of the system and the product of the pressure and the volume. Enthalpy is a state function. We talked about state functions before, where it doesn't matter how you got there, it's just how much enthalpy you have at the moment, right? So that's so enthalpy is a state function. So we have enthalpy is equal to our internal energy plus our pressure times our volume at a given set of conditions. Okay, but normally we're not usually looking for enthalpy by itself. We're usually looking for enthalpy change in a reaction. This will tell us the amount of energy that's being absorbed or released during a reaction, and that's more useful for us in chemistry. So our delta H is essentially going to equal Q at constant pressure, because if we look at our change in internal energy, our change in internal energy was equal to Q plus W, right? But W has a change in volume that we're using. So if we're just looking at a constant volume, right, and a constant pressure, we don't need this W. So essentially, delta E is equal to Q, and delta H is equal to delta E plus our pressure times our change in volume. But again, we're not messing with this. So if our enthalpy is equal to our change in internal energy and our change in internal energy is equal to our heat, then we can set our change in enthalpy equal to our Q of our reaction at constant pressure. Okay, and usually our change in enthalpy and our change in internal energy are similar in value. The only time they're really going to be different is if we have reactions that are either producing or using large quantities of gas, because then we're going to have to take into a change in pressure or a change in volume. But usually delta H is pretty much equal to delta E, which is going to be the same as Q. Okay, I know there's a lot of variables going around. The thing that makes those all not equal, though, is if we have, like I said, large quantities of gas being produced or used up during a reaction. So again, we're going to look at our change in enthalpy, right, delta H. And when delta H is positive, that is heat being absorbed by the system. Because remember, again, we're setting delta H is essentially equal to Q. And so if Q is positive, right, that means heat is being absorbed. So same, delta H is positive, heat is being absorbed. When reactions absorb energy, we call them endothermic reactions. And when delta H is negative, right, if delta H is negative, that means that Q is negative, which means that heat is being released by the system. And these reactions that release heat are called exothermic reactions. So we can use our delta H value, just like we use our Q value, to tell us whether something is exothermic or endothermic. Typically, you will see delta H given for a reaction. It's usually called the heat of the reaction or the energy released in a reaction, but it will be as a delta H value. And again, if it's positive, it'll be an endothermic reaction. If it's negative, it'll be an exothermic reaction. There is a stoichiometric relationship between moles of a reactant and our delta H value, our change in enthalpy. So this change in enthalpy here goes for 1 mole of propane. When we burn 1 mole of propane, it will release this amount of energy. When 5 moles of oxygen are used up in this reaction, it will burn, you give off this amount of energy. When 3 moles of carbon dioxide are produced in this reaction, it will give this amount of energy, right? So this is all stoichiometric. So we can use this, delta H for, 1 mole of this is equal to this as an equality. And we can use this as a conversion factor when we have train tracks, right? Our dimensional analysis for our stoichiometry. So here we have 1 mole of propane will give off negative 2,044 kilojoules. So when we write these dimensional analysis, we can use it with our kilojoules on the top and 1 mole on the bottom, or vice versa, 1 mole on the top and kilojoules on the bottom, just depending on how we are going to need to use this. Same, like I was saying before, for 5 moles of oxygen, that will also give off negative 2,044 kilojoules. So again, we can use it with kilojoules on the top and 5 moles on the bottom, or 5 moles on the top and kilojoules on the bottom. And we could do this for carbon dioxide and water as well. So let's go ahead and see this in action. This says how much heat is evolved in the complete combustion of 3.2 kilograms of propane. So this is the same reaction from the previous slide. Now we're going to use it to see how much heat is evolved. So we have kilograms of propane, so we need to turn that into grams of propane so that we can turn it into moles of propane, so we can use this stoichiometric relationship between moles of propane and kilojoules. So let's go ahead and try this out. So we have 13.2 kilograms of propane, and we know that for every 1 kilogram of propane, there are 1,000 grams of propane. So now that we have it in grams, we can go ahead and convert to moles. So there are 44.11 grams in 1 mole of propane. And now we can go ahead and use this balanced chemical equation, right? For every 1, right, because there's a 1 here, imaginary 1, for every 1 mole of propane that we burn up, we are getting negative 2,044 kilojoules, right? So that means that we have 2,044 kilojoules of energy being released. So if we go ahead and math all this out, we get negative 6.12 times 10 to the 5th kilojoules of energy being released. It's a lot of energy, okay? If you don't like scientific notation, I'll write it down here as well. But that's a lot of energy that's being released. So this is how we would use our mole relationship to stoichiometrically calculate how much energy is being released during a reaction. Okay, our last topic for today is how we can use a calorimeter to measure delta H, to measure our enthalpy of a reaction. And the reason that we would use this is because reactions are typically done in an aqueous solution, and they're done at constant pressure. So again, we can set that delta H value equal to our Q of our reaction because we are at constant pressure. So we're not worrying about any changes in pressure or changes in volume. The reason that they are at constant pressure is because they are open to the atmosphere. And by that, right, I mean, I know that they are closed, but they're not, they're not airtight, right? We have some wiggle room with where the thermometer is and the stir rod is, so some gas could escape. Obviously, we're going to try and keep it all in there, but they are at constant pressure. They are open to the atmosphere. So we'll typically use these nested styrofoam cups, right? These coffee cup calorimeters. And again, we're going to set negative Q of the reaction is equal to Q of the solution. So all of the energy being released by the reaction will be absorbed by the solution. So notice I said solution here rather than the water. Okay, most of our solution will be water, but there's stuff dissolved in it, right? The stuff that's doing the reacting, our solute, has been dissolved in water. Okay, so the way that we will calculate this is that our negative Q of the reaction, right, the energy that's being released during a reaction, just because most times they are exothermic, will be our mass of our solution, so altogether, anything that's dissolved, times our specific heat of our solution. Usually this will be 4.184 because it's usually going to be pretty much the same as water. And then our delta T of our solution, and we'll monitor that using our thermometer here. If this was an endothermic reaction, we would simply make our Q of the reaction positive and our Q of the solution negative. So we would just flip the signs. Okay, so we'll have our mass of our solution, specific heat of our solution, change in temperature. Using all of that, we can calculate how much heat was released by the reaction, and then we can use that to calculate our delta H of the reaction by dividing our Q by moles. Okay, so we'll see an example of this right now. So this says, what is the delta H of the reaction per mole of magnesium for the reaction below? So we have our magnesium is reacting with hydrochloric acid to produce aqueous magnesium chloride and hydrogen gas, which will just kind of bubble off and leave. So it says if 0.158 grams of magnesium reacts in 100 milliliters of solution and changes the temperature from 25.6 degrees Celsius to 32.8 degrees Celsius. So we are having an exothermic reaction here, and the way that we can tell our reaction is exothermic is because the temperature of the solution increased. So that means our solution absorbed a bunch of water, which caused the temperature to increase. So I know that my reaction is exothermic because our solution increased in temperature. For this, we're going to assume the density of the solution is 1 gram per milliliter, and the specific heat of the solution is 4.18 joules per gram degree Celsius. So these, right, this is the density of water, this is the specific heat of water, and that will usually be what we use because most of the solution is water. I do have one note here. We're not going to include the mass of magnesium in the mass of the solution because it's a solid. Right? And so this solid here is not dissolved in our solution. We're just looking at the aqueous portion. So that'll be our hydrochloric acid. So let's go ahead and calculate this out. So we know that our solution is going, or our reaction is going to be exothermic because, right, our solution increased in temperature. So our negative Q of the reaction is going to equal Q of the solution, which means that our negative Q of the reaction is going to equal MC delta T of our solution. Okay, so since our density is 1 gram per milliliter, if we have 100 milliliters of our solution, for every 1 milliliter, we have 1 gram. Oh, and actually these are 1.00, my apologies. So that gives us 100 grams of our solution. Okay, and then we have our specific heat, and we can calculate our change in temperature. So we have our negative Q of our reaction is equal to 100 grams times 4.18 joules per gram degree Celsius, and then we're always going to do T final minus T initial. So 32.8 degrees Celsius minus 25.6 degrees Celsius. And this is going to give us 7.2. And the reason I'm including that is because that's going to limit our significant figures in the answer. So we can only have 2 significant figures because out of our subtraction, we're getting 2 significant figures. So our negative Q of the reaction is 3.0 times 10 to the third joules. And we're actually going to want this in kilojoules. So we're going to say, okay, this is 3.0 kilojoules. So our negative Q of the reaction is equal to Q of the solution. So then we can say, okay, well, Q of the reaction then is negative 3.0 kilojoules. So if our solution absorbed 3 kilojoules of energy, that means our reaction released 3 kilojoules of energy. Our last step, I'm going to actually do this at the top, is to turn our grams of magnesium into moles of magnesium. So we have 0.158 grams of magnesium, and we'll use our molar mass of magnesium to convert that into moles. So we will get that we have 0.00650 moles of magnesium. So now we can calculate our delta H value back down here. Delta H is in kilojoules per mole. So that will be our negative 3.0 kilojoules per 0.00650 moles of magnesium. And when we divide those up, we get that that means we have 460 kilojoules per mole of magnesium. And that would be our answer. So again, we're going to use calorimetry to calculate our Q of our reaction, right? We're going to calculate our MC delta T of our solution. That'll give us Q of our solution, which will tell us Q of our reaction because they're always equal and opposite. We can convert that to kilojoules and then divide by moles to get our answer for our delta H value, our enthalpy of our reaction. Oops, and it appears I've dropped a negative. This will be negative 460 kilojoules per mole. Always check the sign of that delta H value. If you know it's supposed to be exothermic, make sure your answer ended up negative, which I just did. If you know it's supposed to be endothermic, make sure your answer ends up positive. We have one more example for today. This is kind of our trickiest example here. It says, what will be the final temperature of the solution in a coffee cup calorimeter if 50 milliliters of a sample of 0.25 molar hydrochloric acid is added to 50 milliliters of a sample of 0.25 molar sodium hydroxide? It says the initial temperature is 19.50 degrees Celsius and the enthalpy of the reaction is negative 57.2 kilojoules per mole of sodium hydroxide. Again, we're going to assume these solutions are mostly water. So we have 1 gram per milliliter for the density and 4.18 joules per gram degree Celsius for our specific heat. Okay, so there's a lot going on here. What I would always start off with is write a reaction. We know that sodium hydroxide is a base and it's going to react with hydrochloric acid, right, which is an acid. Acid plus base always gives us a salt and water. So water will be one of the products. And then our sodium and our chlorine will end up together as sodium chloride. Okay, so that's always a good place to start. We know that all of, these are aqueous. This is a liquid, and this will be aqueous. Okay, so that's a good place to start. We have, if you'll notice, we have a volume and a molarity of two different things. So I would always go through and check to make sure that there is no limiting reagent. Okay, so I'm going to do that really, really quickly. So if we have, and I'm just going to use it to calculate moles of water, see how much moles of water were produced from each one. So we have 0.05 liters of sodium hydroxide. And for every 1 liter of sodium hydroxide, this is using the molarity, we have 0.250 moles of sodium hydroxide. And using our balanced chemical equation, for every 1 mole of sodium hydroxide, we would produce 1 mole of water. So if sodium hydroxide was limiting, then we would produce 0.0125 moles of water. So we can do the same thing with hydrochloric acid. You can notice here that the numbers are the same, and there's still a 1-to-1 ratio, so this will come out actually exactly the same, but I'll go through it just to show you. So we take our volume of hydrochloric acid and our molarity of hydrochloric acid to turn this into moles. And we know that for every 1 mole of hydrochloric acid, we will produce 1 mole of water based on that balanced chemical equation. So we have 0.0125 moles of water. So there's no limiting reagent here, so we don't have to worry about that, which is great. If there was a limiting reagent, then we would need to take that into account when figuring out how many moles of sodium hydroxide will actually be used. And the reason we care about the sodium hydroxide is because they gave us the energy per mole of sodium hydroxide here. So for every 1 mole of sodium hydroxide that's being used up, we are going to get negative 57.2 kilojoules of energy being released. Okay, so we'll go ahead and we'll take this 0.0500 liters of sodium hydroxide, and we're going to use that stoichiometric relationship from before. So we're going to first use our molarity to turn this into moles. And then using that enthalpy of our reaction here, we know that for every 1 mole of sodium hydroxide that's reacted, we are going to get negative 57.2 kilojoules of energy being released. So the energy released in this reaction is negative 0.715 kilojoules, or negative 715 joules. Okay, so again, using this, our negative Q of the reaction is equal to our Q of the solution. So if we have a negative 715 joules being released during the reaction, that means the energy absorbed during the reaction is going to be 715 joules, positive. So our Q of our solution is going to be 715 joules, because they're always equal and opposite. So now we can go through, and now that we have our Q of the solution, right, we can use that here, so we can have 715 joules is equal to MC delta T for our solution. So we have 715 joules. Our mass of our solution, right, we're going to get from our volumes, and we're going to use our density. So we have 50 milliliters of one of our liquids and 50 milliliters of the other. So we have total 100 milliliters of an aqueous solution. And our density, right, so we have 100.00 milliliters, and our density is 1 gram per milliliter, so that means we have 100 grams of our solution. Okay, we've just lost a couple significant figures along the way because of our density. So we have 100 grams. Our C value is going to be the same as for water, 4.18 joules per gram degree Celsius. And then our change in temperature, right, is going to be TF minus our initial temperature of 19.50 degrees Celsius. So if we go ahead and start solving this, we'll get 715 is equal to 418 times our TF minus 19.50. And again, I've just kind of dropped all of my units for now. They get a little messy. You're welcome to include them if you like. I know that my temperature is going to end up though in degrees Celsius, so I've just dropped them for the time being. So now we'll go ahead and divide both sides by 4.18. We'll get 1.71 is equal to TF minus 19.50, which means that TF is going to equal 21.21 degrees Celsius. Okay, so this is how we would do one of these trickier problems when we have two different aqueous solutions that are being added together. The trick here is to make sure that your mass of solution is going to include both of your solutions that you're adding. Again, typically our specific heat of our solution is going to be the same that it is for water, and we're going to use our density to get our mass. The key here, as always, is that the negative Q of the reaction is going to equal our Q of the solution. And so that's it for today's lecture. So today we covered bomb calorimetry, we covered the enthalpy of a reaction and that stoichiometric relationship between moles and energy being released. And then I showed you how we can use calorimetry in order to calculate our delta H of our reaction, our enthalpy of our reaction. So keep working on these problems. It's a lot of fun with math and just getting used to solving them. There are lots of practice problems in your Chapter 6 lecture worksheet. So keep working, send me any questions you have, and I will see you all next time.